Okay. Hello, everybody. My name is Hugo Zbinden. I'm from the University of Geneva, and I have the honor to chair this session of contributor talks on QKD. We have three speakers: Joseph Ho from Heriot-Watt, Robert Trenny from University of Vigo, and Peter Brown from ENS in Lyon. We will start with Joseph. I remind you that you can ask questions via Slack, or you can also raise your hand and ask a question. But please ask a question at the end of the three talks. And so then maybe if you put it on Slack, you should indicate to whom you would like to address the question. Okay, then please, Joseph, you can start.
All right, thank you so much. One moment. Okay, well, thank you so much. So my name is Joseph Ho, and today I'll be giving a talk titled Experimental Quantum Conference Key Agreement using a photonic graph state. This is work that has been done in collaboration with my colleagues listed here. Okay, so quantum conference key agreement is a cryptographic task that allows end users to share a common secret key. This can then be used for applications like group-wide encryption. And so broadly speaking, there are sort of like two approaches that you can achieve this conference key. The first, and perhaps more familiar to most here, is to essentially use two-party conference key quantum key distribution to first share the keys in pairwise fashion. So here in this conference setting, we might have three users, Alice, Bob, and Charlie. And essentially, Alice and Bob can share a key first, and then Alice and Charlie shares a key second. At the end, Alice holds two keys and has to perform an extra step in order to transform these keys for a conference setting. And so we will refer to these sort of approaches as 2QKD, as they rely on these two-party primitives to generate the keys first. And an alternative approach is to instead use genuine multi-party entanglement, which can be shared between the end users. And with an appropriate protocol where security can be proven, they can arrive at the key directly. And so this sort of approach we will be calling NQKD. And basically the idea behind this talk is to sort of look more closely at these two different approaches. So just as a kind of quick summary for what NQKD entails, we can kind of quickly consider, four users arranged like so. And there's a quantum server that can basically share multi-party entangled states. And so when GHZ states might be that particular state, one possible protocol that can make use of it in order to produce these conference keys is the so-called MBB84 protocol. This was recently proposed and proven secure, including finite key analysis with finite key effects, shown in these two papers. And it just has like kind of four main steps. You share a multi-party GHZ state, perform one of two types of measurements, either in the Z or the X measurements, and use those, a subset of those outcomes to estimate the security parameters, and then perform multi-user, error correction and privacy amplification to arrive at, a common conference key. And so we did this experimentally, preparing the GHZ states and measuring in the appropriate outcomes. And we've basically observed this effect in the asymptotic limit for, asymptotic key rates, and also in the finite key regime. But moving beyond this, we were interested to see how would conference key agreements sort of behave in quantum networks, where you would have multiple users who are connected who might want to therefore establish conference keys. And so in this sort of setting, the idea would be to share entangled resource states in order to perform conference key agreement. And then the two approaches that we described earlier boils down to, can we essentially share GHZ states to implement NQKD directly? Or how do we go about distributing bell pairs to implement 2QKD? And recently, one of the approaches sort of solving this issue is to make use of graph states in a so-called network routing technique. And in this work, we basically adopt this methodology in this sort of setting where we have 6 users, and we've labeled 4 users again who wish to perform conference key agreement, Alice, Bob 1, Bob 2, and Bob 3. And there are 2 additional non-participating nodes, Charlie and Debbie. And the idea is to basically use this graph state to be able to distribute either a GHZ state directly between the group of 4 users here, or the necessary bell pairs to implement 2QKD. Just to kind of hammer this home a bit, so we're saying basically with this starting 6-photon graph, there exists a set of local operations that we could perform that allows us to basically extract this 4-photon star graph, which happens to be equivalent to a GHZ state up to some local rotation. And so this is what allows us to essentially perform the NQKD variant for the conference key agreement. Similarly, one can show by using the same starting resource state and local operations, there are 2 other ways where we can arrive at different entanglement resources, namely bell pairs that spans the group of 4 users. And this is essentially how we will implement the 2QKD variant of conference key agreement. And so the key takeaway here is we can see, right, if we have a single copy of this starting state, we're able to arrive at a conference key directly for the NQKD approach, while the 2QKD approach requires at least 2 copies in this particular arrangement in order to obtain the same single conference key bit. And so this is inherently where this advantage is going to be observed most noticeably. And so in the lab, we basically set up, an experiment to kind of see this. I won't go into the details, but what we essentially do is we prepare this 6-photon graph in the lab, and we implement the necessary local operations on the graph in order to distill the different entanglement resource states, which is then used to implement the different approaches to conference key agreement. So for more information, do check out the longer talk on all of this. But for now, I'll just summarize. Basically, what we did here was we proposed a 6-photon graph in order to implement the 2 different variants for conference key agreement. This is by distributing a GHZ state or sets of bell pairs. And then we measured the noise parameters of these resource states in order to see the performance of each of these approaches. And basically what we found is that in all cases that we've observed here, where they started with the same network resource state, the NQKD was always able to outperform the 2QKD approach. And I think that's my time. Thank you very much.
Thank you very much. As I said, the questions will be at the end of the third talk. So then please, Robert, get ready for your talk. So Robert will talk about the asymptotic performance of coherent one-way quantum key distribution.
Okay, so thank you very much. I hope you can see my screen.
Yeah, maybe you can. Yeah, perfect. Now.
Okay. It's a bit slow, sorry. So thank you very much for the floor. And in this talk, I'm going to talk about the asymptotic performance of the coherent one-way quantum key distribution, or the COW, in other words. And of course, this is going to be a high-level version of the video that I prepared for this conference, but for the details, please see that video. So let me jump right into it. Basically, one severe difficulty in QKD is the fact that we don't have, or it's really challenging to realize high performance and high quality single photon sources. And in order to approximate these in a lab or in real life, what we essentially use is weak coherent pulses. And with this, it opens up the possibility for the so-called photon number splitting attack due to the multi-photon pulses included in this state, in which a possible eavesdropper can basically split off 1 photon for herself, and essentially obtaining the same information as the intended party of the quantum communication. So this is a severe limitation, as the original BB84 with weak coherent pulses without any advanced technique. It has a secret key rate scaling of eta square, where eta is basically the system's transmittance. And originally it would be with eta, so it's a pretty bad thing to let happen to the our QKD protocol. So one type of solution, or a kind of countermeasure against this, among many others, but I won't go into the details, is basically to have protocols that check the coherence between the received signals, this also constitutes a group of protocols, but one of them is the so-called COW, or coherent one-way QKD protocol. And this is a pretty a popular one, and we can see that already long distance experiments have been performed using this scheme, and also it is used in commercial products as well. But the problem before the problem with this scheme was that its security status was not established completely prior to our work, because there were only known upper and lower bounds on its asymptotic performance. And as we can see here, there was a gap between that two. Even though it was the thing, it has been commercialized, and long distance experiments have been performed. And the community hoped this protocol to have the better scaling that is linear in the systems transmittance, because there were also known lower bounds against collective attacks. And for some type of protocols, they are equivalent in the asymptotic case of infinite number of sent signals. So basically the community had high hopes regarding this relatively simple protocol. But in this work, we basically designed an attack which can be used to show that this is not the case. Actually, the protocol in its current formulation, it has diverse scaling that is quadratic in the systems transmittance. And let me just point out two weak points of this protocol. So the first is that the signal states are linearly independent, which makes unambiguous state discrimination possible for a possible eavesdropper. And in this case, basically the eavesdropper can avoid misidentifying signal states. And also another weak point is that we can find vacuum passes in the signals. So this can already also be leveraged by an eavesdropper to avoid breaking the coherence when she's performing this attack. And this attack is basically an intercept recent type of attack. So it falls into the category of general attacks, where Eve basically measures out all the signal states coming from Alice, and based on the results, she prepares new signals that she sends to Bob via lossless channel. And this attack can be converted into an upper bound on this protocol. Here I just want to show the result. I won't go into the details, but we can see that this gives an upper bound on the secret key rate of this protocol, and we can see that asymptotically scales quadratically with the system's transmittance. And with this, I would like to conclude. So we saw that the asymptotic scaling of this protocol is quadratic in the systems transmittance. That renders this inappropriate for long distance QKD, long distance point-to-point QKD, basically. And we also can look at this protocol as an example where coherent or general attacks are actually more powerful than collective attacks. And thank you very much for your attention, and I will look forward to your questions later. Thank you.
Thank you very much, Robert. So we're already coming to our last presentation, which will be given by Peter Brown from Lyon, and he will talk about device-independent lower bounds on a conditional von Neumann entropy. Please, Peter.
Thank you. You can hear me? Right. Yes, so first of all, thanks to the organizers for the opportunity to speak here. I'm going to present some joint work with Hamza and Omar, and this work is available on the archive with this archive number here. So in device independence, we typically have the following scenario where we have two or more black box untrusted devices that we can interact with classically. We can give them inputs and we can receive outputs from them. And we assume during these interactions that the devices cannot communicate with one another. And over many interactions, we maybe observe something about the conditional distribution of the outputs given the inputs, or maybe just some function of this distribution like a Bell inequality violation. Okay, and we know that if the devices in this setting violate a Bell inequality, that they must be producing randomness. And this observation leads us to build on top of these non-locality tests, so-called device-independent protocols for randomness generation or even key distribution. And when we think about a cryptographic protocol, we have to consider the possibility of an adversary. So for example, we now allow the state that was shared between the devices in order to violate the Bell inequality to also be entangled with some adversary system. And the adversary can keep this system and use it to gain information about the outputs of our devices. And when we want to analyze the proof security of these protocols or analyze the performance of these protocols, what we really want to compute is the rate of the protocol. And so very loosely, this just means the number of random bits or the number of key bits that we generate per interaction with our devices. And you can think about computing the rate as an optimization problem, and it takes the following form. We want to minimize a conditional von Neumann entropy over all devices that are compatible with the statistics that we observe in the experiment. Okay, so you can really think about this as allowing the adversary to choose any quantum systems here that are compatible with whatever we observe in our experiments. And they choose them such that they maximize their information about the outputs of our devices. And if you have different protocols, you might have different objective functions here, but they're really all just conditional von Neumann entropy. Okay, and this optimization problem here is quite difficult to solve. First of all, it's non-convex, and second of all, we don't have a bound on the dimension because we're working device independently here. So this state could, for example, be infinite dimensional. And yeah, so a naive attempt to solve this optimization quickly runs into issues. But in this work, we develop a general numerical technique to actually solve, or not solve, but lower bound these rate calculations. And in particular, what we do is we introduce a sequence of quantities, which we just call HM here, such that HM is always a lower bound on the conditional von Neumann entropy, and these HMs tend to the conditional von Neumann entropy as M tends to infinity. Okay, and if you replace the conditional von Neumann entropy in your rate calculations with this HM, then the resulting optimization problem we can show can be approximated efficiently using techniques like the NPA hierarchy, which allow us to compute these approximations using the semi-definite programming. Okay, and what we find in practice is that the rates that we get from this technique, from this method, are actually close to optimal when we know the optimal bound on the rates. The technique itself tends to be more efficient than previous numerical approaches that have been proposed recently. And it also applies in a sort of wider scope in the sense that the results still hold when the systems here are infinite dimensional. Okay, so let me briefly present some of the numerics. So for example, if we constrain our devices by some winning probability in the CHSH game, and we ask what's the amount of bits that we can generate from, for example, Alice's device from the perspective of Eve, then in this case, we actually know a tight bound on the rates of the protocol. So this is given by this red dotted curve. And what we find is that as we move through our sequence of HMs, we actually quickly converge on this bound. So by the time that we get to m equals 8, we actually agree with this known tight bound up to several decimal places. So this shows that our technique can at least be optimal in certain cases. And we also looked at bounding QKD rates, for example. So in this plot, we see this red curve is a QKD protocol, DI-QKD protocol based on the CHSH game again. And we compared it with some protocols where we calculated the rates using our technique based on constraining the devices by their full distribution. So what we found is that in general, everywhere our technique does a lot better than this protocol based on the CHSH game. And kind of what's interesting about this plot is maybe where these rate curves drop to 0, because this tells us sort of a noise threshold beyond which we can actually perform DI-QKD in an experiment. And this red curve, for example, based on the CHSH game, drops to 0 around about the same point as this blue curve. But what we found is that using our technique together with this pre-processing technique that Ernest mentioned in his talk yesterday, we can actually drop the detection efficiency thresholds down to around 80%.
And this is extremely interesting from the perspective of experiments, because this is well within the regime of current photonic experiments. And this prompts the question now of whether DI-QKD is actually feasible in a current experiment. So with that, I thank you for listening and encourage you to look at the extended talk for more details.
Thank you very much. So we have a few minutes time for questions. I didn't get a question via Slack, so if you have a question, maybe you still have a chance to raise your hand and ask the question directly. Maybe I can start with one question for Joseph. So you said that your conference key agreement, you can make it either with different bell pairs or with these graph states, or CHZ sets, CF states. But do you need entanglement? I think you could also do it just with many QKD links based on weak coherent states.
Yeah, so I think that's an excellent question. So basically the kind of motivation then, right, is in sort of future quantum networks where the idea would be, long distance QKD over, multiple nodes where you need states to be compatible with, say, quantum memories. Entanglement would probably be the sort of optimal choice there. So you can actually share these states, in various different configurations. And so I think here for us to sort of establish like this comparison in our network primitive, we've assigned like both the NQKD and 2QKD approaches to employing entanglement as the resources in order to perform each of the protocols. And so, yeah, we do kind of enforce using bell pairs when we're talking about the 2QKD for this particular comparison versus if we're doing NQKD and deriving the GHZ states.
Okay, thank you very much. Is there another questions for Joseph? I got a question in the meantime by Jan Boa Zhang from Peter Brown. And the question is, can your technique be used to bound the sandwiched Rayleigh entropy?
Unfortunately not. We do have a paper, our previous work, which you could use to bound the sandwich Rayleigh entropies via the geometric Rayleigh entropies. But in this work, we go for a direct bound on the von Neumann entropy, so we don't know how it relates to one of the alpha entropies actually. But this is an interesting, maybe old problem to try and solve.
Okay,
great. Thank you.
I hope I had a bit trouble to understand you, Peter. I don't. Maybe I was the only one, but I quite have got it. So, Jan Boa, did you get a response? Yeah.
Yeah, I heard the reply from Peter. Yeah, I'm satisfied. Thank you. So maybe later, yeah, I would like to know more details of your talk. Thanks.
Okay. Well, I got another question for Peter by Vardan. Are the results generalizable to GHZ game as well?
Yes. Our results apply to any Bell inequality that you could want to impose on your devices, or more generally, any linear constraints on the distribution of the devices it applies to.
Okay, thank you. Well, I see Anthony appearing on my screen. Do you have a question? No, you're just...
No, I don't.
Okay, good. So is there another question for one of the speakers? Well, maybe I can ask the question for Robert. So you showed that the scaling with loss is very bad for this cow system. Did you think about a patch, how you could repair the system?
Yeah.
Improvement that it would be better?
Yeah, actually, there are many ways to do so. And Marcos is actually, as far as I know, is working in this direction. But just to say a couple of examples, for example, because in this cow protocol, only the QBER and the visibilities are monitored. One can extend the monitored quantities because this attack well, severely modify some other detection events, for example, the detection of decoy states, for example. But since that is not monitored in the protocol itself, it's if the protocol is run like in its original version, then it's not noticeable for the parties. Or another option could be to employ more states that the parties emit to make unambiguous state discrimination more difficult. And yeah, that's just a couple of examples too. But I don't know how easy fixes are these to actually implement these extensions. Probably Marcos can say more about that. I don't know.
Okay, would you like to comment on that, Marcos?
Hello, good morning or afternoon or evening to everyone. So this is Marcos Curti. Yeah, as Robert said, there are various possibilities. For instance, the idea of enlarging or extending the number of states might not be so difficult already by, one can show that already by adding just one additional state that could be just vacuum. That seems to be not too difficult in the current chaos setup. One could recover an close to linear scaling, let's say. Of course, also measuring more detection rates beyond the QBER and the visibilities also help, although in this case, it would be more difficult, or at least it's not clear exactly how to include this information to obtain actually lower bounds, let's say. So in the sense that if we include this if we put constraints on if that he must match the expected values for more detection rates, then we see that the upper bounds again move to close to linear with the system transmittance, but it's unclear how to translate this in feasible lower bounds. However, the idea of adding more states seems to be a kind of a straightforward way to move forward. Yeah.
Thank you. Is there another question for one of the speakers? There's somebody's raising his hand. Jan Boa, you can ask your questions, please.
Hello. I don't know if I was supposed to speak right now, but I was unmuted.
Okay, so Federico, you have a question? Yes, go ahead.
Yes, yeah. It's a question for Robert. I wanted to, so as far as I remember, collective attacks and coherent attacks were proven to be equivalent in the asymptotic regime under certain conditions. And for what I remember, I think that proof is valid for finite dimensional systems. So clearly it does not apply to the COW protocol. And you showed that is not the case. So I was wondering if your result, basically it's the first counterexample that collective and coherent attacks are equivalent in the asymptotic regime for infinite dimensional systems. Are you aware of any other counterexample?
No, the honest answer is no, I don't know. Mm-hmm. Sorry.
So maybe it is. I also don't know, of course, the whole literature, but I remember that this equivalence was there under certain conditions, and you clearly showed that there are cases where that is not the case.
Yeah, but unfortunately, I'm not aware of. But this doesn't mean that it's the first example.
No, of course. But yeah. Okay, thank you.
Anyway, thank you.
Okay, thank you. Well, in the meantime, we got another question by Gilles. Please, Gilles, you can.
Yes, thank you. Thank you, Hugo. This for Robert. I was just wondering if your attack is at all feasible with current technology or anything foreseeable technology, or is it purely theoretical at the moment?
I think, yeah, it's a good point. At the moment, it's theoretical, but it's a good direction to explore if the measurement is actually implementable. That because we obtain if Eve measures signal by signal, then we obtain the optimal unambiguous state discrimination technique can be obtained analytically, and But of course, it's still an open question if it can actually be implemented, and so now it's on the theory ground only.
And do you feel it would be easier to implement than building a full-fledged quantum computer?
Well,
I know it's not this.
That's a good one. Yeah, I don't know.
No, that's fair enough.
Probably.
Okay. Ernest, you can ask your question yourself. Sorry that you're on Slack. Yeah.
Thanks. So yeah, just to follow up on the question regarding the collective versus coherent text for the COW protocol, I assume it's kind of because you can't apply the definity theorems, but is it because of, I would have assumed it's because there's no permutation symmetry rather than the dimension issue?
Well, it can be, yeah.
Do you have a sense of whether one of these might be a more significant issue to overcome here?
Well, I didn't look into that, so
okay,
not really, but yeah.
Okay, thank you very much.
Well, thank you.
Thank you. Maybe a last question or comment by Marcos.
Hello, yeah, it was regarding two of the questions that were asked to Robert. First, about the feasibility of the attack. So, of course, we cannot say right now that it's feasible, but we believe it's strongly feasible because it's a very simple attack in the sense that if just have to measure directly the signals sent by Alice, and then just prepare new signals and send to Bob. So which means that doesn't require any storage of quantum information, whatever. So the only question is whether the optimal unambiguous state discrimination measurement is easy to perform with current technology or not, that we didn't explore that yet. However, one could think on simple ways just to also unambiguously discriminate the signals that might not be optimal, but still will produce this kind of bad scaling. So I wanted to say that I think the attack is very feasible. And then regarding the coherent and collective question, as Robert said, we didn't explore into that. I'm also, at least to my knowledge, is the first example, but I don't know if it is actually the case where we can see clearly that collective attacks are strongly much powerful than, coherent attacks are much more powerful than collective ones, because we see that this upper bound on the coherent or provided by the coherent attack scales quadratically with eta, while we have lower bounds against collective that scale linearly with eta. But we didn't explore yet why, and this is definitely a very interesting question.
Okay, thank you. Well, I suppose we have to close this session. Well, let's thank all our speakers. And you can meet them. You go on the platform. You can meet them in the meeting rooms and ask further questions. Thank you, everybody, very much, everybody. See you later.